At this very moment, a beam of light is racing toward Alpha Centauri. It will not arrive for more than 4 years. Nothing humanity has ever built has ever completed that journey. Tonight, we're going to examine one of the oldest assumptions our civilization has ever made. We believe that every impossible journey eventually becomes possible. Give humanity enough time, enough knowledge, and better technology, and every frontier will eventually give way. History seems to support that belief. Every generation has carried us farther than the one before it, turning yesterday's impossibilities into ordinary achievements. We learned to cross oceans that once divided civilizations. We learned to fly through skies that once belonged only to birds. We left Earth and stood on the surface of another world. Looking back, the pattern feels almost inevitable. Whatever lies beyond our reach today simply becomes tomorrow's engineering problem. It is a belief that quietly shapes the way we imagine the future, which is why, when people ask whether humanity will someday reach another star, the answer feels almost automatic. Maybe not this century, maybe not even the next, but eventually, yes. Tonight, we're going to examine the possibility that this belief is wrong. Not because our technology will stop advancing. Not because humanity will lose its curiosity. But because the universe may contain limits that no civilization can engineer its way around. That possibility brings us to Alpha Centauri. It is the closest stellar system beyond our Sun. Every serious conversation about interstellar exploration begins here because there is nowhere easier to go. Before humanity dreams of exploring the Milky Way, settling distant worlds, or becoming a civilization that moves freely between the stars, it must answer one question. Can we reach the nearest star? If the answer is yes, then the stars remain open to us. If the answer is no, then many of our greatest visions of the future begin to unravel. Interstellar travel is no longer just another engineering challenge waiting for a better spacecraft. It becomes a test of whether intelligent civilizations can overcome the fundamental architecture of the universe itself. At first, the problem appears surprisingly simple. Alpha Centauri is a little more than 4 light-years away. We hear that number so often that it begins to sound familiar. 4 light-years. It feels like a distance we should be able to understand. Our minds instinctively treat it like any other journey, assuming that bigger engines, faster spacecraft, and future discoveries will eventually make it manageable. That assumption feels perfectly reasonable because every journey throughout human history has followed the same pattern. As technology improves, distance becomes less important. What once required months eventually requires days. What once required days eventually requires hours. Progress has always compressed the world around us. Without realizing it, we expect the universe to behave the same way. We assume that the immense gap between the stars is simply another version of the oceans our ancestors once feared, a challenge that seems overwhelming today but will become ordinary tomorrow. The problem is that space refuses to follow the rules our intuition was built to understand. Human beings evolved on a planet where every meaningful journey existed within a world only a few thousand kilometers across. Everything our ancestors experienced fit comfortably inside that scale. Mountains looked enormous. Oceans seemed endless. Entire civilizations could rise and fall without ever seeing what lay beyond the horizon. Our intuition evolved for that world, and only that world. The universe is different. From the perspective of the cosmos, the distances that shaped all of human history are almost insignificant. The emptiness between one star and the next belongs to a completely different scale of reality. We can read the numbers, we can memorize them, we can perform the mathematics, but truly understanding them is something else entirely. Long before engineers begin designing spacecraft, our intuition has already failed. That failure lies at the heart of one of the greatest misunderstandings in astronomy. We often assume that reaching another star is simply a matter of waiting. Someday, we imagine, future generations will look back at our spacecraft the way we look back at the earliest airplanes, remarkable for their time, but hopelessly primitive by modern standards. It is an appealing story because history has rewarded that kind of optimism again and again. But history only describes what happened within the tiny neighborhood of a single planet. The universe never promised that the same pattern continues forever. There is a profound difference between overcoming a difficult challenge and confronting a fundamental limit. The closer physicists have examined the journey between the stars, the more they have realized that this distinction may define the future of our civilization. Because the greatest obstacle between humanity and another star may not be the spacecraft we have yet to build. It may be the scale of the universe itself. That is why the journey to Alpha Centauri is about far more than reaching one destination. It is the first test of a much larger question. Are the stars truly places we will someday visit? Or are they lights we will spend eternity observing from afar? The answer reaches far beyond rockets, engines, and ambitious space missions. It touches every dream humanity has ever imagined about spreading through the galaxy. It even forces us to reconsider one of the oldest mysteries in science. If intelligent civilizations exist throughout the Milky Way, why does the galaxy appear so silent? Perhaps the answer is not that life is extraordinarily rare. Perhaps the distances between the stars are simply far more unforgiving than our intuition has ever allowed us to believe. Over the next 2 hours, we're going to rebuild that intuition from the ground up. We'll leave behind the comforting scales of everyday life and begin looking at the universe on its own terms. We will explore what modern physics really says about distance, speed, energy, and the extraordinary cost of crossing the space between the stars. But before we can ask whether humanity will ever reach Alpha Centauri, we first have to answer a much simpler question. A question almost everyone believes they already understand. What is a light year, really? There is a reason almost every conversation about interstellar travel begins with the phrase 4 light years. It sounds familiar, comfortable even. We hear the term so often that our brains quietly file it away as something we already understand. After all, we know what a year is, and we know what light is. Put the two together and the meaning feels obvious. But that confidence is misleading, because a light year is one of the most misunderstood ideas in all of science. Despite its name, it has nothing to do with time. A light year is a measurement of distance. The distance light travels through the vacuum of space in one entire year. That definition is technically simple, yet it hides a reality so enormous that the human mind instinctively shrinks it into something far smaller. We memorize the words, but we rarely understand the scale they represent. To appreciate that scale, we first need to understand the thing doing the traveling. Light is not simply fast, it is the fastest speed the universe allows. In a single second, light travels almost 300,000 kilometers. That is fast enough to circle the Earth more than 7 times before 1 second has passed. While you finish reading this sentence, a beam of light could have traveled from Earth to the Moon and back several times. Nothing in everyday life prepares us for numbers like these. Commercial aircraft, rockets, bullets, and even the fastest spacecraft humanity has ever launched are almost motionless by comparison. Light does not belong to the same category of motion as the machines we build. It operates on a completely different scale, and because it is so extraordinarily fast, we naturally assume that it makes the universe feel small. In reality, it reveals the exact opposite. Imagine standing on Earth with a perfectly focused laser aimed at the Moon. The instant you press the switch, the beam begins crossing the empty space between our planet and its only natural satellite. It does not arrive immediately. Even moving at the fastest speed the laws of physics permit, the light needs a little over 1 second to complete the journey. That may not sound impressive at first, but it should. The Moon is our closest celestial neighbor, and even here, space is vast enough that light cannot cross it instantly. Already, the solar system is asking us to abandon the intuition we developed on Earth, where almost every distance in our daily lives feels immediate. Now extend that same thought to the sun. Every ray of sunlight warming your skin today began its journey more than 8 minutes ago. When you watch the sunrise, you are not seeing the sun as it exists in that exact moment. You are seeing the sun as it was over 8 minutes in the past. If our star were to disappear this instant, a purely hypothetical scenario, the Earth would continue orbiting normally, and the sky would remain bright for those same 8 minutes because neither light nor information can travel faster than light itself. The universe never presents itself to us in real time. Everything we observe arrives with a built-in delay. The greater the distance, the older the information becomes. This is one of the strangest truths in astronomy, yet we rarely stop to think about it. Looking at the moon is looking a little over 1 second into the past. Looking at the sun is looking more than 8 minutes into the past. Looking at the outer planets means seeing them as they were tens of minutes or even hours ago, depending on where they are in their orbits. Every telescope, no matter how advanced, is fundamentally a machine for looking backward through time. The night sky is not a live broadcast of the universe. It is a collection of messages that have been traveling across space for varying lengths of time, each one carrying a snapshot of the past. So far, however, everything we have discussed has remained inside our own cosmic neighborhood. 1 second, 8 minutes, a few hours. These are delays that still fit comfortably within human experience. You can imagine waiting 8 minutes. You can picture an hour passing. Your intuition still has something familiar to hold on to. That sense of familiarity is about to disappear. Because everything we have measured so far, the Earth, the Moon, the Sun, and even the distant planets, exists inside a tiny island of space surrounding our star. We have not yet stepped beyond the solar system. And once we do, the numbers stop growing in ways our minds can naturally follow. They explode into a scale where even light, the fastest traveler in the universe, begins to look astonishingly slow. That is the moment when a light year stops being a scientific definition and becomes something far more unsettling. It becomes the first clue that the nearest star is not simply far away, it belongs to a different scale of reality altogether. The moment we leave the solar system, our everyday intuition stops being useful. Inside our planetary neighborhood, distances may seem enormous, but they are still measured in minutes or hours at the speed of light. That familiarity quietly tricks us into believing the same pattern continues forever. We assume that if light reaches the sun in 8 minutes, then the nearest star cannot be that much farther away. Our brains expect another reasonable step. Instead, they encounter a cliff. Between the edge of our solar system and the nearest star lies an expanse of emptiness, so vast that every comparison from ordinary life begins to fail. It is here that the phrase, 4 light years, finally reveals what it has been hiding all along. Imagine leaving Earth aboard a spacecraft capable of traveling at the speed of light. This is impossible according to everything modern physics tells us, but imagine it anyway. The moon would disappear behind you in just over a second. The sun would be 8 minutes behind you. Within a few hours, the giant planets would begin falling into the darkness. In a little over 5 hours, you would pass the orbit of Neptune, the most distant major planet in our solar system. By human standards, you would have completed the greatest journey in history before the end of a single day. Yet the nearest star would still be almost unimaginably far away. You would continue moving at the fastest speed the universe allows for days, then weeks, then months. A full year would pass, then another. Only after more than 4 years of continuous travel would you finally arrive at Alpha Centauri. Even light, the fastest thing that exists, cannot make that journey quickly. That is the detail most people never truly absorb. We often hear that Alpha Centauri is only 4 light years away, and the word only slips into the sentence almost automatically. But there is nothing small about a distance that requires light itself to travel for more than 4 years without slowing down, without stopping, and without encountering traffic, weather, or obstacles of any kind. Light moves at the ultimate speed limit built into reality, and even it needs years to bridge the gap. The problem is not that our spacecraft are too slow. The problem is that the universe is staggeringly large. To understand how misleading our intuition can be, Imagine shrinking the solar system until the Earth's orbit fits inside the size of a coin. The planets would still seem comfortably close together, and crossing from one world to another would appear manageable. Now ask yourself where Alpha Centauri would be on that same scale. It would not sit just beyond the edge of the table. It would not even remain inside the same city. The nearest star would still be thousands of kilometers away. Every classroom diagram, every textbook illustration, and every simplified animation quietly compresses these distances until the stars appear to exist just beyond the planets. They do this because the real scale is impossible to fit on a page. Useful diagrams teach us where things are, but they accidentally hide how astonishingly far apart they really are. This is why astronomers rarely think in kilometers when discussing the universe. The numbers become so large that they stop communicating anything meaningful. Saying that Alpha Centauri is roughly 40 trillion kilometers away is mathematically correct, but the figure overwhelms the imagination. It is simply a collection of digits with no emotional weight. The light year was invented because even scientists needed a unit capable of describing cosmic distances without drowning in zeros. Ironically, the new unit solved the mathematical problem while creating a psychological one. The numbers became easier to write, but the true scale became even easier to underestimate. Once you begin seeing the universe through this perspective, an uncomfortable realization starts to emerge. Every ambitious plan for interstellar exploration immediately collides with the same reality. It does not matter whether we imagine chemical rockets, nuclear engines, fusion propulsion, or technologies that have not yet been invented. Before we discuss how to cross the distance, we must first accept what the distance actually is. Every serious conversation about reaching another star begins with humility because the universe demands it. We cannot solve a problem that we have failed to understand. And this is precisely why Alpha Centauri matters so much. It is not merely another destination waiting to be explored. It is the first great test of whether intelligent civilizations can ever escape the tiny islands of light they call home. If the closest star already stretches the limits of physics, engineering, and human imagination, then every more distant destination becomes exponentially harder. The journey to Alpha Centauri is not simply the first step toward the stars. It is the question that determines whether there can ever be a second step at all. Before we can ask how humanity might overcome that challenge, we need to confront another uncomfortable truth. Distance is only one part of the problem. Even if we somehow learn to cross the darkness between the stars, we would still face another obstacle, one that is every bit as unforgiving as distance itself. Because in the universe, speed is not just difficult, speed has limits. By now, the problem seems obvious. The stars are unimaginably far away. Alpha Centauri is not separated from us by millions of kilometers or even billions, but by a distance so vast that light itself requires more than 4 years to cross it. It is an intimidating number, but it still feels like an engineering problem. After all, history has taught us the same lesson over and over again. Whenever a destination seemed impossibly distant, humanity found a way to travel faster. We walked until we learned to ride. We rode until we learned to sail. We sailed until we built engines. Engines became aircraft, aircraft became rockets, and every breakthrough made the world feel a little smaller. Progress has always compressed distance by increasing speed. It is only natural to assume that the journey to another star follows exactly the same pattern. If 4 light years is too far today, then perhaps all we need is a spacecraft that moves fast enough. It is an assumption that feels so reasonable most people never question it. In fact, nearly every science fiction story begins with the same idea. Somewhere in the future, humanity invents a revolutionary engine, builds a faster spacecraft, and suddenly the stars become accessible. The details change from one story to another, but the solution is always the same. Faster travel solves the problem. We carry that expectation into real science without even realizing it, because every experience in our everyday lives reinforces it. If driving takes too long, we fly. If a computer is too slow, we build a faster one. If a rocket is inefficient, we design a better rocket. Human progress has always rewarded speed. The universe, however, does not. That is one of the most profound differences between life on Earth and life on a cosmic scale. On Earth, speed is usually a technological limitation. Faster engines, stronger materials, and better designs allow us to move farther in less time. The laws of physics rarely stand in our way. They simply wait for us to become clever enough to use them more efficiently. Space appears similar at first glance, but hidden beneath that familiar pattern is a rule unlike anything we encounter in ordinary life. It is not a limitation created by our technology. It is woven into the fabric of reality itself. There is a speed beyond which the universe simply refuses to let anything travel. That speed is the speed of light. People often describe it as the fastest speed in the universe, but that description is actually incomplete. It makes the speed of light sound as though it won some kind of cosmic race, as though another discovery might eventually reveal something even faster. Modern physics suggests something far more unsettling. The speed of light is not simply the fastest speed we have measured. It is the maximum speed at which information, energy, or cause and effect can move through space itself. It is not a technological barrier waiting to be overcome. It is one of the rules that defines how the universe operates. This idea is surprisingly difficult to accept because nothing in our daily experience prepares us for it. Imagine asking someone in the 19th century whether trains could travel 100 kilometers per hour. Many would have considered it impossible. A century later, airplanes were flying several times faster. Today, spacecraft leave Earth at speeds those early engineers could never have imagined. History has conditioned us to believe that every speed limit eventually turns out to be temporary. Again and again, yesterday's impossible velocity became today's routine journey. The speed of light is different. No civilization has ever discovered a loophole. No experiment has revealed an exception. Every observation we have made of the universe, from the smallest particles to the largest galaxies, points toward the same conclusion. Reality itself is built around this limit. It is as fundamental as the existence of space and time. At first, that may not sound like a serious problem. After all, no spacecraft has ever come remotely close to the speed of light anyway. Surely the solution is simply to keep improving until we get there. Build a more efficient engine, develop a better fuel, wait another few hundred years for technology to mature. That expectation seems perfectly reasonable because we instinctively imagine speed as a straight line. We picture ourselves moving faster and faster until, eventually, we arrive at light speed. But the universe does not allow that journey to unfold the way our intuition expects. As strange as it sounds, the closer an object moves toward the speed of light, the more difficult it becomes to make it go even faster. Every small increase demands dramatically more energy than the one before it. Progress no longer behaves the way it does on Earth. Instead of rewarding each improvement with predictable gains, the universe begins pushing back. And that is where the journey to another star becomes far stranger than almost anyone imagines. Because the problem is no longer building a faster spacecraft. The problem is convincing the universe to let you accelerate at all. The closer scientists studied the behavior of light, the stranger the universe became. For centuries, people assumed that speed worked the same way for everything. Throw a ball harder and it travels faster. Build a stronger engine and a vehicle accelerates more quickly. Improve the technology and eventually almost any speed should become possible. It was a simple idea, and for everyday life it worked remarkably well. Nothing suggested that nature would suddenly change the rules. Then in the early 20th century, Albert Einstein proposed something extraordinary. He suggested that the speed of light was not just another speed. It was woven into the structure of reality itself. Space and time were not fixed stages on which the universe performed. They were part of the performance. Stretch one and the other responded. The faster an object moved, the more unusual reality itself became. At first, this sounded absurd. It seemed to contradict common sense in almost every possible way. Yet over the past century, experiment after experiment has confirmed the same conclusion. Relativity is no longer a bold hypothesis. It is one of the most thoroughly tested descriptions of nature ever developed. Modern GPS satellites correct for relativistic effects every single day. Particle accelerators observe them constantly. Even the technology guiding airplanes and smartphones depends on calculations that only work because Einstein was right. This is where our intuition begins to fail completely. Imagine pushing a child on a swing. The harder you push, the faster the swing moves. The relationship feels predictable. More effort produces more speed. Human experience teaches us that this pattern should continue forever. If something is not moving fast enough, simply apply more energy. Eventually it will reach whatever speed you want. The universe quietly disagrees. As an object moves faster and faster, every additional increase in speed becomes more expensive than the one before it. At low speeds, the difference is almost impossible to notice. Cars, airplanes, and rockets all behave almost exactly the way our instincts expect. But as a spacecraft approaches a significant fraction of the speed of light, the rules begin to change. The energy required to gain even a tiny increase in velocity starts rising dramatically. The closer you get to light speed, the steeper the climb becomes. It is as though the universe slowly transforms a gentle hill into an almost vertical mountain. This is one of the reasons the speed of light is often compared to a horizon. You can move closer and closer to it, but reaching it is an entirely different matter. Every improvement becomes smaller while the energy required grows larger. Imagine climbing a staircase where every step is twice as tall as the one before it. At first the climb feels manageable, then exhausting. Eventually the next step becomes so enormous that no amount of effort can lift you high enough. That is not a failure of determination. It is the geometry of the staircase itself. The same principle applies to interstellar travel. Suppose humanity invents an engine far beyond anything we possess today. It accelerates a spacecraft to 10% of the speed of light. That achievement alone would represent one of the greatest engineering triumphs in history. At that speed, the journey to Alpha Centauri would still take more than 40 years. So we naturally ask the next question: why not accelerate to 20%, or 50, or 90? Because each increase demands far more than simply building a better engine. It demands vastly more energy. And eventually, the numbers become so extreme that they begin to challenge not just engineering, but civilization itself. A mission to another star is no longer measured only by the size of the spacecraft. It is measured by the amount of energy an entire planet can produce. Every additional percentage point closer to the speed of light carries a cost that grows faster than our intuition expects. Long before we reach the ultimate speed limit, the practical barriers become almost overwhelming. This is the uncomfortable truth hidden behind every dream of interstellar exploration. We often imagine that the greatest challenge is inventing the right technology, yet physics asks a much harsher question. Even if humanity possessed unlimited ingenuity, will we possess enough energy to use it? That question changes everything. Because the journey to Alpha Centauri is no longer simply about crossing an enormous distance. It becomes a problem of energy on a scale our civilization has never attempted before. Every proposed spacecraft, every revolutionary engine, and every ambitious mission must answer the same unforgiving question before it ever leaves Earth. Where will the energy come from? And that is where our journey takes its next turn. Because before humanity can dream of building a ship capable of reaching another star, we first have to understand why every engine we have ever invented is nowhere near powerful enough. The challenge is no longer speed alone. It is energy itself. There is a natural assumption we all make when we hear about faster spacecraft. We imagine the challenge is building a better engine, a more efficient fuel, a revolutionary design. It is the same pattern that has driven transportation throughout human history. Every major breakthrough has come from finding a more powerful way to move. Steam replaced muscle. Jet engines replaced propellers. Rockets carried us beyond the atmosphere. Looking back, it feels as though every problem eventually surrendered to better technology. So it is tempting to believe that reaching another star is simply waiting for the next great invention. The problem is that physics does not measure progress the way history does. On Earth, building a vehicle that travels twice as fast is usually an engineering challenge. It requires stronger materials, better aerodynamics, or a more efficient engine. The costs increase, but they remain understandable. Interstellar travel follows an entirely different set of rules. As a spacecraft approaches the speed of light, the relationship between speed and energy begins to change in ways that defy everyday intuition. Every additional increase in velocity demands disproportionately more energy than the one before it. Progress no longer follows a straight line. The closer you move toward light speed, the steeper the cost becomes. Imagine pushing a heavy boulder across perfectly flat ground. At first, every push produces noticeable movement. Now imagine that with every meter the boulder travels, it becomes slightly heavier. Your effort remains the same, but the progress becomes smaller. Eventually, you are pushing with everything you have, yet the boulder barely moves at all. That image is not a perfect description of relativity, but it captures something important. Near the speed of light, nature begins resisting every attempt to accelerate further. The universe is not simply asking for a better engine. It is demanding astonishing amounts of energy. This is why physicists rarely ask, "Can we build a faster spacecraft?" Instead, they ask a far more difficult question: where will the energy come from? Because every proposal for interstellar travel eventually arrives at the same obstacle. It is not the spacecraft. It is not the engine. It is the energy required to make the journey possible. To appreciate how serious this problem is, consider the spacecraft humanity has already built. The fastest probes ever launched are extraordinary achievements of engineering. They have crossed billions of kilometers, explored distant planets, and escaped the immediate influence of the sun. Yet compared to the speed of light, they are barely moving. At their current velocities, reaching Alpha Centauri would not take decades. It would not take centuries. It would take tens of thousands of years. Entire civilizations could rise, flourish, disappear, and be forgotten before such a spacecraft arrived. The difference between our fastest technology and the speed required for practical interstellar travel is not a small gap waiting to be closed. It is an entirely different category of challenge. Naturally, scientists have imagined more powerful engines. Nuclear propulsion could produce far more energy than chemical rockets. Fusion engines, if they can ever be built reliably, promise even greater performance. Antimatter contains more energy per unit of mass than any known fuel. Each idea represents a remarkable leap beyond today's technology, and every one of them has been studied seriously by physicists and engineers. Yet despite their differences, they all confront the same uncomfortable reality. None of them escapes the laws of physics. More advanced propulsion can shorten the journey, but it cannot remove the extraordinary energy demanded by relativistic speeds. This realization forces us to rethink the scale of the problem. We often imagine interstellar travel as the next chapter of space exploration, an ambitious project that naturally follows the moon landings and robotic missions to Mars. In reality, the leap is far greater than that comparison suggests. The difference between reaching Mars and reaching Alpha Centauri is not like the difference between crossing one ocean instead of another. It is closer to the difference between taking your first step across a room and attempting to cross an entire continent in a single stride. The numbers do not simply become larger. They become almost disconnected from ordinary human experience. This is also why so many concepts that sound convincing in science fiction become far less practical under the scrutiny of physics. A fictional spacecraft can accelerate continuously without concern for fuel, waste heat, or energy production because the story demands it. Reality is less forgiving. Every kilogram of fuel must be accelerated along with the spacecraft. Every engine produces waste. Every source of power has limits. Every improvement introduces new engineering problems. Solving one challenge often creates another. Interstellar travel is not a puzzle with a single missing piece. It is a chain of interconnected problems, each one amplifying the next. And yet, despite all of this, scientists have never stopped searching for solutions. That persistence reveals something remarkable about our species. Humanity has always been drawn toward horizons that seem permanently out of reach. The purpose of physics is not to discourage exploration. It is to reveal the true nature of the obstacles standing before us. Sometimes those obstacles can be overcome. Sometimes they cannot. The only way to know the difference is to understand them honestly. As our understanding of the universe has grown, one conclusion has become increasingly difficult to ignore. The challenge of reaching another star is not defined by a single impossible barrier. It is defined by several barriers layered on top of one another. Distance is the first, the speed of light is the second, energy is the third. But hidden behind all of them is an even stranger consequence of relativity, one that seems almost impossible until you realize it has already been measured countless times. Because the faster you travel through space, the more strangely time itself begins to behave. By this point, the challenge seems almost impossible. The nearest star is separated from us by an unimaginable distance. The speed of light stands as a limit that no object with mass can simply cross, and every attempt to approach that limit demands extraordinary amounts of energy. It is easy to look at these obstacles and reach a simple conclusion. Interstellar travel is impossible, yet modern physics offers a stranger answer. The universe does not make the journey impossible. It changes the journey in ways that almost no one expects. Everything up to this point has treated time as though it were fixed. Seconds pass, minutes become hours, years become decades. We experience time as something universal, flowing at the same pace for everyone, everywhere. It feels as reliable as gravity itself. Whether you're standing still, driving down a highway, or flying across an ocean, time appears to move with perfect consistency. Every clock seems to agree with every other clock. It is one of the deepest assumptions human beings make about reality, because nothing in everyday life gives us a reason to doubt it. The universe, however, has never promised that assumption was true. In 1905, Albert Einstein proposed an idea so extraordinary that it completely changed our understanding of reality. According to his theory of special relativity, space and time are not separate things. They are woven together into a single fabric known as spacetime. That alone was revolutionary, but the consequences were even stranger. If space and time are connected, then changing one inevitably changes the other. The faster an object moves through space, the differently it experiences time. Not because its clock is broken, not because of an illusion, but because time itself is behaving differently. At first glance, this sounds impossible. Common sense tells us that a second is a second, no matter who measures it. Imagine placing two perfectly identical clocks side by side. You would expect them to remain synchronized forever. If one clock suddenly began falling behind the other, you would naturally assume it was defective. Yet relativity predicts exactly that outcome under the right conditions. If one clock remains on Earth while the other travels at an enormous fraction of the speed of light, they will no longer agree when they are reunited. The traveling clock will have measured less time. It will quite literally have experienced a shorter journey through time itself. This is known as time dilation, and despite sounding like science fiction, it is one of the best tested predictions in all of modern physics. Scientists have measured it using incredibly precise atomic clocks carried aboard high-speed aircraft. They observe it every day in particles traveling close to the speed of light inside powerful accelerators. Even the satellites that make the global positioning system possible must constantly correct for relativistic effects. Without those corrections, GPS errors would grow by several kilometers every single day. The phone in your pocket works because Einstein's theory accurately describes how time behaves. The important point is not that time slows down in some mystical sense. It is that time becomes personal. Two observers following different paths through the universe can genuinely experience different amounts of time between the same two events. Neither observer is wrong. Neither clock is broken. Reality simply refuses to give everyone the same answer. This is one of the moments where human intuition reaches its limit. Throughout our lives, we have treated time as the one thing that never changes. We can imagine space stretching across unimaginable distances. We can imagine faster machines and more powerful engines, but imagining time itself flowing at different rates requires abandoning one of the oldest assumptions we have about existence. It feels impossible because evolution never prepared our brains for a universe that behaves this way. On Earth, the effect is so incredibly small that it passes unnoticed. Only when objects move at truly extraordinary speeds does relativity reveal itself. Now return to the journey toward Alpha Centauri. Imagine that, centuries from now, humanity finally builds a spacecraft capable of traveling at an astonishing 99% of the speed of light. Such a machine would represent one of the greatest engineering achievements in history. From Earth's perspective, the voyage would still require years. Light itself needs more than 4 years to make the crossing, so even a spacecraft traveling slightly slower would take longer than that. But for the people aboard the ship, something remarkable would happen. Their clocks would not measure the same amount of time as the clocks back on Earth. The faster they traveled, the more dramatically those two experiences would diverge. For the crew, the journey could feel surprisingly short. For the people they left behind, it would be much longer. At first, this sounds like a gift. Relativity appears to offer an escape from the crushing distances between the stars. If time passes more slowly aboard the spacecraft, perhaps interstellar travel is not as hopeless as it first seemed. Perhaps the universe has hidden a shortcut inside its own laws. It is a beautiful idea. But like almost everything else in physics, it comes with a price. Because while the travelers may arrive feeling as though only a few years have passed, the Earth they return to may no longer be the Earth they left behind. At first, time dilation sounds like the solution humanity has been searching for. If the crew experiences less time than the people on Earth, then perhaps the enormous distances between the stars are not as overwhelming as they first appeared. Perhaps the universe has quietly provided a loophole. Travel fast enough, and a journey that would normally consume decades could feel like only a few years. It is one of the most beautiful consequences of Einstein's theory, and for a moment it almost feels as though physics is finally working in our favor. But the universe never gives without taking something away. The key to understanding time dilation is realizing that it does not make the journey shorter for everyone. It only changes how the journey is experienced by the travelers themselves. Imagine two clocks beginning at exactly the same moment. One remains safely on Earth while the other leaves aboard a spacecraft traveling at an enormous fraction of the speed of light. Neither clock is broken. Neither is running incorrectly. Each simply follows a different path through space-time. When the spacecraft eventually returns, the two clocks no longer agree. The travelers have aged less than the people who stayed behind. They have not entered the future through magic. They have simply experienced less time. This idea is often illustrated with what physicists call the twin paradox. Imagine identical twins. One remains on Earth while the other departs on a relativistic journey to another star. The traveling twin eventually returns expecting to reunite with the sibling they left behind. Instead, they discover someone much older waiting for them. If the voyage was extreme enough, they may not even return to the same generation. Children have become grandparents. Friends have lived entire lives. Entire careers, cultures, and nations have come and gone. For the traveler, only a handful of years may have passed. For Earth, decades or even centuries may have slipped away. That is one of the strangest consequences of relativity. The greatest sacrifice of interstellar travel may not be the danger of the journey. it may be separation from time itself. Now imagine this reality on the scale of an entire civilization. Humanity finally succeeds in building a spacecraft capable of reaching Alpha Centauri at an extraordinary fraction of the speed of light. The crew trains for years, says goodbye to everyone they know, and begins the greatest expedition in history. From their perspective, the mission unfolds exactly as planned. They conduct research, maintain the spacecraft, watch distant stars slowly brighten, and eventually arrive at humanity's nearest stellar neighbor. They may even believe that they will one day return home to celebrate one of the greatest achievements our species has ever accomplished. But Earth has been keeping a different clock. Every message sent from home becomes older. Every familiar voice slowly disappears. Parents who stood on the launch platform are gone. Brothers and sisters are gone. Entire generations have lived and died while the spacecraft continued its silent journey through interstellar space. Languages have evolved. Governments have changed. Scientific discoveries have reshaped civilization. By the time the explorers finally return, they may arrive not in the future they imagined, but in a world that barely remembers the century in which they were born. This is why many physicists describe relativistic travel as a one-way journey into the future. Unlike the time machines of science fiction, there is no way to return to the past. Relativity allows time to unfold differently for different observers, but it never reverses its direction. The travelers can leap forward relative to Earth, yet they can never reclaim the years that passed without them. Every mission becomes a quiet act of farewell. The farther they travel and the faster they move, the greater the distance that opens not only across space, but across history itself. Perhaps this is the price hidden inside every dream of reaching another star. We often imagine the greatest challenge as surviving the vacuum of space or building engines powerful enough to cross the darkness. Yet relativity reveals a more personal obstacle. Exploration has always meant leaving home behind, but never before has it required leaving behind your own time. The explorers who step onto another world may still be human, but the civilization they return to may no longer feel like their own. They would become strangers, not because they traveled too far, but because history continued without them. Suddenly, the journey to Alpha Centauri becomes more than a technological challenge. It becomes a philosophical one. What does it mean to leave Earth if you can never truly come back? Is reaching another star still a victory if everyone you hope to tell about it is already gone? Would you volunteer for a mission knowing that, by the time you returned, your family, your culture, and perhaps even your nation would exist only in history books? These are no longer questions about rockets. They are questions about what it means to be human. And yet, despite everything we have learned, humanity has never stopped imagining ways to cross the gulf between the stars. Scientists continue designing engines that have never been built, exploring concepts that seem almost impossible today, and searching for methods that might one day make interstellar travel more practical. The dream survives because curiosity has always pushed our species beyond the boundaries of the familiar. But before we examine those extraordinary ideas, we must confront one final reality. Even if time itself bends in your favor, you still need a spacecraft capable of surviving the journey. By now, the challenge of reaching Alpha Centauri has changed completely. At the beginning of our journey, the problem appeared almost simple. The nearest star seemed like a destination waiting for a better spacecraft. Then the true scale of distance emerged. We discovered that even light needs more than 4 years to make the crossing. We learned that the universe enforces a speed limit that no object with mass can cross, that every increase in velocity demands extraordinary amounts of energy, and that time itself refuses to flow equally for everyone. It would be easy to conclude that the dream of interstellar travel ends there. But engineers rarely stop where physics becomes uncomfortable. Throughout history, humanity has faced problems that seemed impossible until someone asked a different question. Instead of asking how to fly like birds, we built airplanes that obeyed entirely different principles. Instead of asking how to breathe underwater, we designed submarines that carried their own environment with them. Again and again, progress came not from changing nature, but from adapting ourselves to it. That same philosophy has shaped every serious proposal for reaching another star. If we cannot change the laws of physics, perhaps we can change the kind of spacecraft we build. That realization marks one of the biggest turning points in the history of interstellar thinking. Most people imagine a spacecraft the way science fiction has trained us to imagine it. A crew climbs aboard, powerful engines ignite, years pass, and eventually the ship lands around another star. It is a familiar image because it mirrors every journey humanity has ever taken. The travelers who depart are the same people who arrive. But once physicists began calculating realistic travel times, that assumption started to collapse. Even with technologies far beyond anything we possess today, many missions would still last decades. More conservative designs stretched into centuries. Some concepts required 1,000 years or more. At that point, the spacecraft stops behaving like a vehicle. It becomes a world. This is one of the strangest consequences of interstellar travel. The farther the destination, the less important the spacecraft itself becomes. Instead, the focus shifts toward the people inside it. A mission lasting centuries cannot depend on supplies packed at launch. It cannot rely on constant support from Earth. There are no repair stations drifting between the stars, no emergency rescue missions waiting just beyond the horizon, and no possibility of turning back if something goes wrong. Once the engines fade into silence, and the solar system disappears behind the ship, every person aboard becomes completely dependent on a tiny artificial world surrounded by absolute emptiness. Nothing like this has ever existed. The International Space Station, impressive as it is, remains only a few hundred kilometers above Earth. If something critical fails, astronauts can return home within hours. Supplies arrive regularly. Engineers on the ground monitor every system continuously. Even future missions to Mars will still exist inside the protective influence of our own star. An interstellar spacecraft would enjoy none of those advantages. It would be utterly alone. That changes the way engineers think about survival. A ship crossing the void between stars cannot simply carry food. It must produce food. It cannot simply carry air. It must recycle every breath with extraordinary efficiency. Every drop of water becomes precious. Every machine must be repairable using materials already on board. Nothing can be considered disposable because replacements will never arrive. The spacecraft must become a completely self-sustaining ecosystem, a closed world capable of supporting human life year after year, generation after generation. And that may be one of the greatest engineering challenges humanity has ever imagined. Creating a rocket powerful enough to leave Earth is difficult. Creating an entire ecosystem that remains stable for centuries may be even harder. Life on Earth survives because it is supported by a planet of astonishing complexity. Forests recycle carbon, oceans regulate climate, microorganisms silently perform chemical processes that make life possible. Billions of interconnected systems operate continuously, most of them without us ever noticing. Compressing even a tiny fraction of that complexity into a spacecraft is an undertaking unlike anything civilization has ever attempted. Every plant, every bacterium, every recycling system, every habitat module would need to function together with almost perfect reliability. A single long-term failure could threaten everyone aboard. This is the moment where interstellar travel stops looking like a transportation problem. It becomes a civilization problem. Because the question is no longer, can we build an engine powerful enough to reach another star? The question becomes, can we build a miniature world capable of surviving the journey? And once scientists began exploring that question, they arrived at an idea so extraordinary that it completely changed the conversation. Perhaps the people who arrive at Alpha Centauri have not even been born yet. The idea first sounds like something invented for a science fiction novel. Instead of sending a crew that expects to complete the journey, imagine launching a spacecraft, knowing that everyone aboard will live their entire lives without ever seeing the destination. Their children will inherit the mission. Their grandchildren will inherit it after them. Generation after generation will be born, grow old, and die inside a world made entirely of steel, glass, and machinery, while the stars outside change so slowly that no single lifetime can perceive the movement. The people who finally arrive at Alpha Centauri may have no personal memory of Earth at all. For them, the birthplace of humanity would not be home. It would be history. This concept is known as a generation ship, and despite sounding fantastical, it has been studied seriously for decades. Not because scientists believe it is easy, but because it avoids one of the greatest obstacles we have already encountered. If practical interstellar speeds remain beyond our reach, perhaps the solution is not to shorten the journey, but to accept its true length. Instead of asking a human being to survive for hundreds of years, we ask a civilization to do it. The spacecraft ceases to be a vehicle carrying passengers. It becomes an isolated society drifting through interstellar space. That single shift transforms every challenge we have discussed so far. Suddenly, engineering is no longer the greatest concern. Biology, psychology, sociology, and even philosophy become equally important. A generation ship cannot simply keep people alive. It must keep an entire civilization functioning for centuries without outside assistance. Every child born aboard must learn the skills needed to maintain systems they did not build. Every generation must willingly continue a mission they never chose. Every crisis must be solved using only the knowledge and resources available within the ship itself. History offers a warning here. Human civilizations have collapsed under far easier conditions. Empires have disappeared despite fertile land, abundant resources, and contact with neighboring cultures. Languages have vanished. Knowledge has been lost. Entire technologies have been forgotten because the societies that created them could no longer sustain themselves. A generation ship would have none of the advantages that helped civilizations recover throughout history. There would be no trade, no migration, no rescue, and no second chance. If critical knowledge disappeared aboard the ship, there would be nowhere to rediscover it. Imagine a child born 200 years after launch. They have never seen an ocean. They have never felt rain. They have never stood beneath an open sky filled with clouds drifting overhead. Every landscape they know was designed by engineers centuries earlier. Artificial sunlight marks the passing of days. Mechanical systems create the air they breathe. Water flows only because countless pumps and filters continue operating somewhere behind the walls. To that child, the spacecraft is not transportation. It is the entire universe. Now imagine trying to explain Earth. Not through photographs or recorded videos, but through stories. Stories about mountains stretching beyond the horizon, forests that seem endless, oceans so vast that land disappears from sight, and skies filled with billions of stars unfiltered by metal ceilings or observation windows. With each passing generation, those memories become less like lived experiences and more like ancient mythology. Earth slowly transforms from a place into an idea. That realization introduces a question few people ask. Would future generations still believe in the mission? The engineers who launched the ship understood its purpose. They accepted the sacrifices because they volunteered for them. But what about the people born centuries later? They never chose to leave Earth. They never agreed to spend their lives inside an artificial world traveling toward a destination they would never personally reach. Why should they continue repairing aging systems? Why should they dedicate their lives to a mission planned by people who died hundreds of years before they were born? These are not engineering questions. They are questions about human nature. A generation ship would require more than reliable technology. It would require a stable culture capable of preserving purpose across centuries. Education would become as essential as oxygen. Every generation would need to understand not only how the spacecraft works, but why it exists in the first place. The mission itself would have to become part of the civilization's identity. Without that shared purpose, the greatest spacecraft ever built could slowly unravel from within. This is why many scientists believe the hardest part of interstellar travel may never be the engine. It may be sustaining a society capable of surviving extraordinary isolation without losing its knowledge, its cooperation, or its reason for continuing. And even if humanity solved all of those problems, another challenge still waits. Because a journey lasting centuries is not simply threatened by loneliness or mechanical failure. It is threatened by the universe itself. Between the stars lies an environment unlike anything we experience inside the solar system. Tiny particles become deadly projectiles. Invisible radiation never stops. Dust no larger than a grain of sand can strike with the energy of an explosion when relative velocities become high enough. The emptiness between stars is not truly empty. It is a hostile ocean that slowly attacks everything moving through it. Which means that before humanity can dream of arriving at Alpha Centauri, we must first survive the journey through interstellar space itself. By this point, the journey to Alpha Centauri has transformed into something almost unrecognizable. What began as a simple question about reaching the nearest star has unfolded into a chain of challenges unlike anything humanity has ever faced. Distance stretches beyond intuition. Speed collides with the laws of relativity. Energy rises to almost unimaginable levels. Time itself refuses to pass equally for everyone. Even the spacecraft has evolved from a vehicle into an artificial world carrying generations of people through the darkness. It is tempting to believe that we have finally identified every major obstacle. We haven't, because there is another assumption quietly hiding beneath all the others. When people imagine the space between stars, they usually picture emptiness, a perfect vacuum, a silent black void stretching endlessly in every direction. It seems reasonable to think that once a spacecraft escapes the solar system, the difficult part is over. No weather, no gravity wells, no planets to avoid, just an endless expanse of nothing. The universe tells a very different story. Interstellar space is astonishingly empty compared to the environments we experience on Earth, but empty does not mean harmless. Even the darkest regions between the stars contain atoms, microscopic dust grains, high-energy particles, and invisible radiation moving through the galaxy at extraordinary speeds. Under ordinary circumstances, these particles are almost insignificant. On Earth, our atmosphere absorbs most of them before they ever reach the ground. Our planet's magnetic field deflects many of the charged particles arriving from space, acting like an invisible shield that has protected life for billions of years. We rarely notice this protection because it has always surrounded us. The moment a spacecraft leaves the solar system, much of that protection disappears. For the first time in human history, an entire civilization would exist beyond Earth's natural defenses. There would be no atmosphere overhead, no global magnetic field stretching thousands of kilometers into space. Every person aboard would depend entirely on the shielding built into the spacecraft itself. Suddenly, something invisible becomes one of the greatest threats to survival. Radiation. On Earth, we often associate radiation with nuclear reactors or medical equipment, but the universe has been producing radiation long before planets existed. Exploding stars, rapidly spinning neutron stars, black holes, and even our own sun constantly release energetic particles into space. Some travel at astonishing speeds, carrying enough energy to damage living cells, alter DNA, and slowly weaken electronic systems. A short mission may tolerate small amounts of this exposure. A journey lasting decades or centuries is a completely different challenge. Imagine standing outside during a gentle rainstorm. A few drops are hardly noticeable. Stay there for a few minutes and you become wet. Remain there for weeks without shelter, and eventually the continuous exposure becomes dangerous. Radiation behaves in a similar way. The danger often comes not from a single dramatic event, but from the relentless accumulation of countless invisible impacts over enormous periods of time. Every day spent in deep space adds another layer of exposure. Scientists have spent decades studying this problem because even missions to Mars must confront it. Astronauts living aboard the International Space Station already receive significantly more radiation than people on Earth, despite remaining relatively close to our planet. Future crews traveling to Mars will experience even greater exposure because they will spend months outside much of Earth's magnetic protection. Yet compared to a voyage lasting generations, a mission to Mars is almost brief. Now imagine centuries. Every wall surrounding the crew becomes more than a structural component. It becomes a shield separating life from a hostile universe. Engineers must carefully choose materials capable of absorbing energetic particles without making the spacecraft impossibly heavy. Too little shielding and long-term exposure threatens the health of everyone aboard. Too much shielding, and the ship becomes so massive that accelerating it demands even more energy. Every solution creates another trade-off. And radiation is only the beginning. There is another danger hiding inside the darkness, one so small that it seems almost impossible to fear. Dust. On Earth, a tiny grain of dust drifting through the air is harmless. You brush it away without thinking. In interstellar space, that same grain obeys entirely different rules. Remember what we learned about speed. The faster a spacecraft travels, the greater the energy involved in every collision. At a significant fraction of the speed of light, even microscopic particles become extraordinarily dangerous. A dust grain no larger than a grain of sand can strike with devastating force because of the enormous relative velocity between the spacecraft and the particle. This is one of those moments where the scales of the universe quietly overturn our everyday instincts. We naturally fear large objects, asteroids, comets, and planets, because those are the things capable of causing destruction on Earth. During an interstellar journey, the greatest danger may come from objects too small to see. Every second of the voyage, the spacecraft races through a sparse cloud of atoms and microscopic debris accumulated over millions of years. Most particles are incredibly tiny, but the journey is unimaginably long. Over decades, centuries, or even millennia, the number of encounters slowly grows. Each impact removes a little more material. Each collision erodes the protective skin of the spacecraft. Individually, they seem insignificant. Together, they become a constant battle against the environment itself. The emptiness between the stars is not peaceful. It is simply hostile in quieter ways. And once scientists realized just how unforgiving interstellar space could be, another unsettling question emerged. Even if humanity could build the perfect spacecraft, could we build one that survives the journey intact? The obvious solution seems simple. If microscopic particles threaten the spacecraft, then build stronger armor, add thicker walls, reinforce the front of the ship until nothing can penetrate it. It is exactly how we solve similar problems on Earth. Stronger protection usually means greater safety. Interstellar travel refuses to follow that logic. Every additional layer of shielding increases the mass of the spacecraft, and mass is something we have already learned to fear. A heavier ship demands more energy to accelerate. More energy requires more fuel. More fuel increases the mass even further, demanding even more energy in return. Engineers call this one of the cruelest cycles in rocket design. Every attempt to solve one problem quietly creates another. The spacecraft begins chasing its own weight, growing larger and heavier, until the solution itself becomes part of the challenge. This is why designing an interstellar spacecraft is unlike designing any vehicle in human history. A modern airliner can be repaired after landing. A naval vessel can return to port for maintenance. Even spacecraft operating inside the solar system can receive instructions from Earth, and future missions may eventually be supported by orbital infrastructure around Mars or other planets. An interstellar spacecraft has no such luxury. Once it leaves the solar system, there is nowhere to dock, nowhere to refuel, and no possibility of rescue. Every system must continue functioning for decades, centuries, or perhaps even longer without outside assistance. That requirement changes everything. The ship cannot simply survive launch, it must survive time itself. Every pump, every computer, every sensor, every electrical connection, every seal, and every structural component must continue operating in an environment that never stops testing them. Even if each individual part is extraordinarily reliable, enough time guarantees that failures will eventually occur. On Earth, we replace worn components without much thought. During an interstellar mission, replacement parts do not exist unless they were brought from the beginning or manufactured aboard the ship. This is why many engineers believe the spacecraft of the future would need to function less like a machine and more like a living organism. Living organisms constantly repair themselves. Human skin replaces damaged cells, bones heal after fractures. The immune system identifies problems before they spread. Nature survives because it continuously maintains itself rather than waiting for complete failure. A true interstellar spacecraft may need to do the same. Imagine billions of microscopic sensors embedded throughout the hull, constantly searching for tiny cracks long before they become dangerous. Imagine robotic maintenance systems moving silently through hidden corridors, replacing damaged components while the crew sleeps. Imagine advanced manufacturing systems capable of producing replacement parts from raw materials carried aboard the ship. Instead of depending on a single repair crew, the spacecraft itself becomes an active participant in its own survival, constantly inspecting, repairing, and adapting to the hostile environment surrounding it. Remarkably, many of these ideas are already being explored in laboratories today. Self-healing materials, autonomous robots, artificial intelligence capable of monitoring complex systems, and advanced manufacturing technologies are no longer pure science fiction. They remain limited, but they hint at an important truth. The first interstellar spacecraft may not simply be built. It may have to care for itself. Yet even a self-repairing ship cannot eliminate every danger waiting between the stars. The galaxy is not perfectly smooth. While most of interstellar space is unimaginably empty, it is also unpredictable. Clouds of gas drift through the Milky Way. Regions with higher concentrations of dust appear without warning. Powerful stellar explosions send energetic particles racing across the galaxy for thousands of years. Even distant stars occasionally unleash violent eruptions capable of flooding nearby space with intense radiation. An interstellar mission lasting centuries would almost certainly encounter environments no engineer could predict at the moment of launch. Think about that for a moment. The people designing the spacecraft will be trying to protect future generations from hazards that had not even been discovered yet. No explorer in human history has ever faced uncertainty on this scale. The great ocean voyages of the 15th century lasted months. Polar expeditions lasted years. Even the Voyager spacecraft, humanity's most distant machines, remain in communication with Earth. Every interstellar mission would leave behind something much more valuable than supplies or spare parts. It would leave behind certainty. From the moment the spacecraft disappears into the darkness, its crew becomes responsible for solving problems that no one back home can anticipate. Messages traveling at the speed of light would eventually take years to cross the distance between the ship and Earth. Conversations become impossible. Advice arrives long after the emergency has already passed. Every difficult decision must be made by the people aboard, using only the knowledge they possess at that moment. In many ways, the greatest challenge of interstellar exploration is not crossing space. It is accepting absolute independence. And perhaps that is the most remarkable realization of all. The farther humanity travels from Earth, the less important Earth becomes to the success of the mission. Eventually, the spacecraft must become completely self-sufficient, not only physically, but intellectually. It must grow beyond being an expedition supported by civilization and become a civilization in its own right. Only then does another possibility begin to emerge. If we can build a world capable of surviving between the stars, perhaps we no longer need to send thousands of people at all. Perhaps the first explorers of Alpha Centauri will not be ordinary humans. By now, the journey to Alpha Centauri barely resembles the dream most of us imagined at the beginning of this documentary. We started with a simple destination, a nearby star visible in the southern sky, but every layer we peeled back revealed another challenge waiting beneath it. Distance stretched beyond intuition. Speed collided with the laws of relativity. Energy reached almost unimaginable scales. Time itself refused to flow equally for everyone. The spacecraft became an artificial world, and even that world had to survive centuries of radiation, microscopic impacts, mechanical failures, and complete isolation. After everything we have learned, another question begins to emerge. Have we been making the wrong assumption from the very beginning? For more than a century, nearly every discussion about interstellar travel has started with the same image. A spacecraft leaves Earth carrying a crew of astronauts toward another star. It is an image inherited from the history of exploration. Every great journey in our past was defined by the people who made it. Sailors crossed oceans. Pilots crossed continents. Astronauts crossed the space between Earth and the Moon. Naturally, we imagine the next frontier unfolding in exactly the same way. But history has a habit of changing its methods when the scale of the problem changes. Long before human beings walked on the Moon, robotic spacecraft had already explored places no person could survive. Before astronauts orbited Saturn or Jupiter, which they never have, machines were already sending back breathtaking images from worlds billions of kilometers away. Today, some of humanity's greatest discoveries come not from human explorers, but from robotic spacecraft, patiently operating in environments that would kill us within seconds. Without realizing it, we have already accepted an important principle. Sometimes the best explorer is not a human being. That idea becomes impossible to ignore when we begin thinking about Alpha Centauri. Every problem we have discussed so far exists because humans are fragile. We need oxygen, we need water, we need food. We require protection from radiation, comfortable temperatures, stable gravity over long periods, and complex ecosystems capable of supporting life. Every one of those requirements makes the spacecraft larger, heavier, and more difficult to build. Machines ask for far less. A robotic probe does not need fresh air. It never becomes lonely. It does not require sleep, medical care, or psychological support. It does not care whether the journey lasts 20 years or 200. It never complains about confinement, never misses home, and never wonders whether the mission is worth the sacrifice. Once designed correctly, it simply continues its task. From an engineering perspective, that simplicity is incredibly attractive. Imagine removing every habitat module from an interstellar spacecraft. Remove the gardens, remove the sleeping quarters, remove the hospitals, kitchens, recreation areas, and life support systems. Suddenly, the spacecraft becomes dramatically smaller. Its mass falls, its energy requirements decrease. Many of the problems that seemed overwhelming only moments ago begin to shrink. The journey itself has not become easier. The passengers have. This realization has inspired one of the most ambitious scientific ideas ever proposed. Instead of sending people, what if humanity sent machines intelligent enough to explore another star system on our behalf? not simple robots following pre-programmed instructions. Something far more capable. An autonomous scientific explorer that could make decisions without waiting years for instructions from Earth. This is necessary because communication itself becomes one of the greatest obstacles. Even if a spacecraft successfully reaches Alpha Centauri, every message it sends home would still require more than 4 years to arrive. Every reply from Earth would require another 4 years to travel back. A single conversation would take nearly a decade. Real-time guidance becomes impossible. Any machine operating around another star must think for itself. In many ways, that future is already beginning. Artificial intelligence has transformed dramatically over the past few decades. Machines can now recognize patterns, navigate unfamiliar environments, analyze enormous amounts of information, and solve problems that once required constant human supervision. They remain far from human intelligence, but the direction of progress is unmistakable. By the time humanity possesses the engineering ability to launch an interstellar mission, artificial intelligence may have advanced far beyond anything we can currently imagine. If that happens, the first explorer to reach Alpha Centauri may not breathe. It may not eat. It may never even know what fear feels like. And perhaps that is exactly why it succeeds. Yet this possibility raises a question that is far more philosophical than technological. If a machine reaches another star, has humanity truly reached another star? From one perspective, the answer is obviously yes. Every photograph, every measurement, every scientific discovery becomes part of human knowledge. The machine is simply an extension of our curiosity, much like the Voyager spacecraft continues exploring the outer reaches of the solar system today. But there is another perspective. Knowledge is not the same as experience. A robot can analyze the atmosphere of an alien world with extraordinary precision. It can measure gravity, study geology, search for life, transmit breathtaking images back across the darkness. But it will never stand beneath an unfamiliar sky and feel the weight of another world's gravity beneath its feet. It will never look toward a distant sun and realize that Earth has become just another star among countless others. Perhaps that difference matters more than we realize. Because the greatest dream of interstellar travel has never been simply to see another world. It has always been to stand upon one. The question becomes even more complicated when we stop thinking about today's technology and begin imagining the civilization that might actually attempt an interstellar mission. Such a civilization would almost certainly possess artificial intelligence far beyond anything we know today. It might have autonomous factories capable of building entire settlements without human supervision. It might even possess machines able to repair themselves, adapt to unexpected conditions, and continue operating for centuries. At that point, sending a robotic explorer would no longer feel like sending a machine. It would feel like sending an independent intelligence across the stars. For many scientists, that possibility is not only practical, it is inevitable. The harsh reality of interstellar travel seems to favor machines at almost every level. They tolerate radiation far better than humans. They require fewer resources. They can remain dormant for decades without suffering boredom or loneliness. They do not need massive rotating habitats to simulate gravity, nor do they require the complex ecosystems necessary to sustain human life. Every kilogram removed from the spacecraft reduces the energy required for the journey, and every unnecessary system left behind makes the mission slightly more achievable. But there is another idea that pushes this logic even further. Instead of transporting fully grown human beings, what if we transported the instructions for building them? At first, it sounds almost impossible. Yet several researchers have seriously explored concepts that replace living passengers with frozen embryos, genetic material, or even complete digital libraries containing the biological information needed to begin a new human settlement. In this vision, the spacecraft arrives at Alpha Centauri carrying no astronauts at all. Instead, autonomous systems construct a habitat, prepare a safe environment, and only then begin creating the first generation of humans. The people who take their first breath beneath another star would also be the first people ever born there. It is one of the strangest ideas humanity has ever considered. The first child born around another sun would never have seen Earth. They would never have stood beneath a blue sky, listened to rain falling through trees, or watched the moon rise over an ocean. Everything they understood about humanity's birthplace would come from history lessons, archived recordings, and stories preserved across an interstellar journey that ended before they were even alive. From their perspective, Earth would be an ancestral memory, not a home. That thought forces us to confront something deeper than engineering. For thousands of years, humanity has measured exploration by the courage of the people who undertook it. We remember the names of explorers because they personally crossed the frontier. But an interstellar civilization may redefine exploration completely. The greatest mission in history might not involve people leaving Earth at all. It might involve creating entirely new branches of humanity beneath distant stars, civilizations connected by ancestry, yet separated forever by the immense distances of the galaxy. That possibility changes the meaning of the journey itself. Perhaps the goal was never to transport Earth across space. Perhaps the goal was simply to ensure that humanity continued. Yet even this extraordinary vision raises difficult ethical questions. Who decides to create a child on a world millions of kilometers from the planet where our species evolved? What responsibilities would the artificial intelligence caring for that child possess? Could a machine truly replace parents? Could an algorithm teach language, culture, morality, compassion, and everything else that transforms a newborn into a human being? Technology may eventually solve the engineering challenges, but it cannot easily answer the philosophical ones. These questions have no universally accepted answers. And perhaps they never will. Because interstellar travel is no longer asking what we are capable of building. It is asking what kind of civilization we hope to become. There is also a possibility even stranger than artificial intelligence or embryo missions. What if humanity eventually learns to preserve not just its biology, but its mind? For decades, scientists and philosophers have debated whether consciousness could ever be recorded, copied, or transferred into another medium. At present, no evidence suggests that such a feat is possible, and many researchers remain deeply skeptical. But the idea continues to appear because it addresses the same problem every interstellar proposal must confront: human mortality. If consciousness could somehow exist independently of a biological body, a possibility that remains entirely speculative, then journeys lasting centuries might become fundamentally different. Instead of protecting fragile human bodies, a spacecraft might preserve information itself. Today, that idea belongs firmly in the realm of speculation. But history has repeatedly shown that today's speculation sometimes becomes tomorrow's engineering challenge. Whether that future ever arrives is impossible to know. What we do know is this: every serious proposal for reaching another star eventually reaches the same conclusion. The greatest obstacle is not simply the spacecraft. It is us, our biology, our lifespan, our psychology, our need for home. The farther we push toward the stars, the more clearly we begin to see that the universe was never designed around human limitations. And perhaps that is the most humbling lesson of all. For centuries, we believed the greatest challenge would be finding another habitable world. Now we are beginning to realize the greatest challenge may be becoming a species capable of reaching one. But before we decide whether humanity belongs among the stars, there is one final question we cannot ignore. A question that has haunted astronomers for generations. If reaching the nearest star is this difficult, then why does the galaxy appear so silent? For almost everything we have discussed tonight, there is an answer people instinctively reach for: better technology, more powerful engines, smarter computers, stronger materials. History has taught us that whenever humanity encounters an impossible challenge, innovation eventually changes the rules. So after everything we have learned about distance, relativity, energy, and the brutal environment between the stars, one question naturally remains. Have scientists actually tried? Not in novels, not in movies, not in optimistic predictions about the distant future. Have they sat down with the laws of physics exactly as we understand them today and asked a much more practical question? If we had to build an interstellar mission without breaking the known laws of the universe, what would it actually look like? Surprisingly, the answer is yes. Long before reusable rockets, private space companies, or modern artificial intelligence, a small group of engineers and physicists decided to stop dreaming about interstellar travel and start calculating it. Instead of asking what might be possible thousands of years from now, they asked what could be designed using real mathematics, real engineering, and real physics. Every assumption had to survive careful analysis. Every kilogram had to be accounted for. Every source of energy had to obey the same physical laws that govern every spacecraft ever launched from Earth. For the first time, the journey to another star stopped being science fiction. It became an engineering problem. The result was one of the most ambitious studies ever attempted. It was called Project Daedalus. In the 1970s, members of the British Interplanetary Society spent years designing a spacecraft unlike anything humanity had ever imagined. Their goal was remarkably straightforward: build a vehicle capable of reaching another star without relying on warp drives, wormholes, or any other speculative technology. No magical discoveries, no violations of Einstein's theories, only physics that scientists believed could eventually become reality. The spacecraft they designed was enormous. Not merely larger than the rockets we launch today, but larger than almost anything ever proposed in the history of engineering. Fully fueled, it would weigh tens of thousands of tons. It would never launch directly from Earth because no rocket could possibly lift something that massive. Instead, it would have to be assembled in space over many years before beginning its journey into interstellar darkness. Its engine would be powered by nuclear fusion. Fusion is often described as the energy source of the stars because it is the process that allows the sun to shine. Instead of burning chemical fuel like today's rockets, Project Daedalus would ignite tiny fusion pellets at an astonishing rate, producing continuous bursts of energy powerful enough to push the spacecraft to speeds no chemical engine could ever achieve. On paper, it was one of the most efficient propulsion systems serious science had ever considered. And even that wasn't enough. Despite its extraordinary size, despite carrying an energy source more powerful than any rocket ever built, and despite representing the combined efforts of some of the brightest engineers of its time, Project Daedalus would still spend decades crossing interstellar space. Think about what that means. This was not an ordinary spacecraft. It was a machine so ambitious that it stretched the limits of 20th century engineering almost beyond recognition. and yet the nearest stars still refused to become nearby. The journey would outlast political careers. Entire scientific fields would evolve before the mission was complete. Children born on the day of launch could grow old before receiving confirmation that the spacecraft had arrived. Suddenly, the numbers we explored earlier begin to feel real. The distances between the stars are not simply large. They remain overwhelming even after humanity imagines one of the greatest machines it has ever conceived. Perhaps the most fascinating detail about Project Daedalus is what it chose not to carry. There were no astronauts, no rotating habitats, no artificial cities drifting through space, no attempt to protect human life during the voyage. The designers reached a conclusion we have gradually been approaching throughout this documentary. Carrying people would make the mission dramatically more difficult. Life support systems, food production, radiation shielding, gravity, medicine, and every other requirement of human survival would increase the spacecraft's mass until the mission became even less practical. So they removed the humans. The spacecraft would travel alone. Its only purpose would be exploration. It would race across the darkness, study another stellar system, and transmit its discoveries back toward Earth, even though those signals would themselves require years to arrive. For many scientists, this represented the first truly realistic vision of interstellar exploration. Not glamorous, not cinematic, not heroic in the way science fiction often imagines. Just patient, methodical engineering, confronting the universe exactly as it is. But if Project Daedalus proved anything, it was not that interstellar travel had been solved. It proved something far more unsettling. Even our most realistic plans remained almost unimaginably difficult. The spacecraft depended on fusion engines that humanity still has not mastered. It required construction on a scale never attempted in space. It demanded resources, infrastructure, and international cooperation, unlike anything in modern history. Every major component pushed against the edge of our technological abilities. Eventually, one conclusion became impossible to ignore. Project Daedalus had not failed because the mathematics was wrong. It stalled because civilization was not yet capable of building the machine the mathematics described. And yet, something remarkable happened. Scientists did not abandon the dream. Instead, they asked an even more radical question. What if the solution was not building a bigger spacecraft? What if the solution was building an almost impossibly smaller one? That single idea would eventually inspire one of the boldest interstellar projects ever proposed. A mission that would weigh not thousands of tons, but only a few grams. If Project Daedalus represented the largest interstellar spacecraft humanity could realistically imagine, the next great idea moved in exactly the opposite direction. Instead of asking how to build a ship powerful enough to carry thousands of tons across interstellar space, a new generation of scientists asked a far stranger question. What if the spacecraft weighed almost nothing at all? For decades, engineers had struggled against the same mathematical reality. Every kilogram added to a spacecraft demanded more fuel. More fuel increased the spacecraft's mass, which demanded even more fuel in return. It was a cycle that seemed impossible to escape. No matter how advanced the engine became, the spacecraft always carried the burden of its own weight. But weight only becomes a problem if you insist on sending something large. What if you didn't? That simple idea eventually grew into one of the most ambitious scientific proposals ever announced. It is called Breakthrough Starshot. Unlike Project Daedalus, Breakthrough Starshot does not attempt to send astronauts, massive habitats, or even a traditional spacecraft. Instead, its goal is almost unbelievably modest. Send something no larger than a computer chip. Imagine a spacecraft so small that it fits comfortably in the palm of your hand. Attached to it is an incredibly thin reflective sail stretching several meters across. The spacecraft carries no enormous fuel tanks, no giant fusion reactor, and no chemical engines. Instead of pushing itself through space, it allows Earth to provide the acceleration. The concept depends on something that sounds almost impossible. Light. Although light has no mass, it carries momentum. Every photon striking a reflective surface delivers an incredibly tiny push. Normally, that force is so small that it goes completely unnoticed. But if billions upon billions of powerful laser beams were focused onto an ultralight sail, those tiny pushes would combine into an enormous acceleration. Instead of burning fuel, the spacecraft would ride a beam of light. For a few brief minutes after launch, an array of lasers located here on Earth would fire continuously at the sail with extraordinary precision. The beam would push the tiny spacecraft faster and faster until it reached roughly 20% of the speed of light. Pause for a moment and think about that number. 20%. No spacecraft in history has traveled anywhere remotely close to that velocity. At that speed, the journey to Alpha Centauri would no longer require centuries. It could take approximately 20 years. For the first time in this documentary, the numbers begin to feel almost hopeful. A child watching the launch could still be alive when the first images arrived from another star. Compared with every proposal that came before it, Breakthrough Starshot feels almost miraculous. But by now, we have learned to be cautious whenever the universe appears generous. Because every solution hides another problem. The first challenge appears almost immediately. Keeping a laser beam focused on an object moving away from Earth at extraordinary speed is one of the greatest engineering tasks ever imagined. The beam must remain astonishingly precise across enormous distances. Even the slightest error could cause the sail to drift away from the laser, ending the acceleration long before the spacecraft reached its intended velocity. Then there is the laser itself. The system required for Breakthrough Starshot does not exist. It would demand one of the most powerful laser arrays humanity has ever attempted to build, consuming immense amounts of energy while operating with extraordinary precision. Thousands of individual lasers would need to behave as though they were a single instrument. Weather, atmospheric distortion, mechanical vibrations, and countless other factors would all have to be overcome before the first spacecraft could even leave Earth. And even if every one of those challenges were solved, another problem waits at Alpha Centauri. How do you stop? This is perhaps the most overlooked difficulty in the entire mission. Project Daedalus planned to race through another stellar system because slowing down required carrying even more fuel. Breakthrough Starshot faces the same dilemma. The tiny spacecraft reaches such incredible speed that it cannot simply apply the brakes upon arrival. Instead, it flashes through the Alpha Centauri system in a matter of hours. Imagine spending decades crossing interstellar space, only to have your destination disappear behind you before a single day has passed. Every photograph, every scientific measurement, every discovery must be collected during those few precious hours. Then the spacecraft continues drifting forever into the darkness beyond. That single detail reveals something profound. Getting to another star is only half the journey. Remaining there may be even harder. When scientists compare every realistic proposal for interstellar exploration, an extraordinary pattern begins to emerge. The closer their ideas come to obeying the known laws of physics, the smaller the spacecraft becomes. The passengers disappear. Massive habitats shrink into robotic probes. Generation ships become microscopic machines propelled by beams of light. The dream survives, but it changes. After more than a century of serious scientific research, after some of the brightest physicists and engineers on Earth devoted their careers to the problem, the most realistic mission humanity has designed is not a starship carrying explorers. It is a tiny machine, no heavier than a few grams. That should tell us something about the true scale of the universe. The stars are not refusing to be explored because humanity lacks imagination. They are refusing because reality itself is unimaginably demanding. And yet, there remains one final possibility. Throughout this documentary, we have accepted one assumption without ever questioning it: that every spacecraft must travel through space. But what if that assumption is the real limitation? What if the future does not belong to faster engines, or lighter spacecraft, or more powerful lasers, but to a completely different way of thinking about motion itself? Because hidden deep inside Einstein's own equations is an idea so controversial, so mathematically strange, that it appears to cross the stars without ever breaking the speed of light. It is known as the warp drive. In 1994, a Mexican theoretical physicist named Miguel Alcubierre sat down with Einstein's own equations and asked a question almost no one had taken seriously before. Not whether we could build an engine fast enough to approach the speed of light, but whether the speed limit itself could be quietly stepped around. Because here is the detail almost everyone misunderstands about relativity. The speed of light limit applies to objects moving through asterisk space. Nothing with mass can accelerate past that boundary while traveling through the fabric of the universe. But space itself is not bound by that same rule. Space can stretch, space can expand. We already know this because we have measured it happening on the largest scales imaginable. Distant galaxies are currently receding from us faster than the speed of light, not because they are moving through space at impossible velocities, but because the space between us and them is expanding. The galaxies themselves are nearly motionless. The fabric carrying them is what is racing apart. If space itself can expand faster than light without breaking any law of physics, Alcubierre asked, could a spacecraft use that same loophole deliberately? The idea he proposed has since become known as the Alcubierre drive, or more popularly, the warp drive. Instead of accelerating a spacecraft to dangerous, fuel-hungry velocities, you leave the spacecraft essentially motionless relative to the space immediately surrounding it. Then, using an enormous and precisely controlled amount of energy, you contract space in front of the ship and expand space behind it. Picture a treadmill made of the universe itself. The spacecraft sits inside a bubble, a small, stable region of normal space, while everything around that bubble warps. Space ahead shrinks, pulling the destination closer. Space behind stretches, pushing the point of departure away. The bubble, carrying the ship like a passenger riding inside a fold in fabric, moves forward. The brilliance of the idea is that the spacecraft inside the bubble never exceeds the speed of light relative to the space immediately surrounding it. Locally, nothing has broken Einstein's law, but because the space itself is moving, the bubble can cross enormous distances in dramatically less time than light would take through ordinary, unwarped space. A loophole built directly into the architecture of relativity itself. Alcubierre published the mathematics, and the physics community took it seriously, not because anyone believed it was close to achievable, but because the equations were valid. They did not violate general relativity. They were a legitimate solution to Einstein's field equations, the same equations that describe black holes and the expansion of the cosmos. For a discipline that had spent a century mapping out exactly what the universe forbids, this felt like the universe quietly leaving a door unlocked. Then physicists asked the question that always follows an exciting new idea. What would it actually take to build one? The answer was the first sign of trouble. To create the spacetime distortion Alcubierre's equations described, you do not need ordinary matter or energy, no matter how much of it you have. You need something that, as far as every experiment ever conducted has been able to determine, may not exist anywhere in the universe. Negative energy. Negative energy is not simply less energy. It is a region of space where the energy density itself becomes less than zero, less, in a real and measurable sense, than complete nothingness. For decades, this sounded like chalkboard fiction. Then physicists discovered it had actually been measured. The discovery is called the Casimir effect. Take two perfectly flat metal plates and place them a few micrometers apart in a vacuum. Quantum mechanics tells us even a perfect vacuum seethes with virtual particles flickering in and out of existence, a thoroughly confirmed phenomenon observed in particle accelerators daily. The narrow gap between the plates restricts which of these particles can exist there, the way a narrow pipe only lets certain notes resonate. Fewer virtual particles fit in the gap than in the open space around it. The result is a measurable force. The plates are gently pulled together, not pushed from outside, but because the vacuum between them genuinely contains less energy than the vacuum around it. Scientists have measured this directly. Negative energy is real. We have built it in a laboratory on Earth. For a moment, this should feel like the breakthrough the warp drive has been waiting for. It is not. The negative energy produced by the Casimir effect is a fraction of a single Newton, comparable to the weight of a few grains of sand. To warp spacetime around a spacecraft, the scale required is not simply larger. It is larger by a factor that breaks intuition entirely. Early calculations, including some by Alcubierre himself, suggested warping space around a ship would require negative energy equivalent to converting the entire mass of a planet like Jupiter directly into energy. The entire mass of Jupiter, not fuel, not power capacity, the literal conversion of a gas giant into negative energy using a mechanism physics cannot even theoretically describe. In 2011, NASA physicist Harold White reignited the conversation. By optimizing the geometry of the warp bubble, a thinner, more refined shape than Alcubierre's original design, White calculated the energy requirement could drop by orders of magnitude, not from a planet to a moon. From a planet to something closer to the mass of Voyager 1, a few hundred kilograms, converted entirely into negative energy. Still extraordinary, still entirely beyond any technology we possess, but the closest thing to good news the field had received since 1994. NASA's Eagle Works laboratory began running small-scale experiments, attempting to detect even the faintest possible signature of warp field effects using extraordinarily sensitive interferometers. The results were inconclusive. No confirmed detection has ever been published. But for the first time, a national space agency was treating the warp drive as legitimate, if extraordinarily distant, physics. Even with White's optimization, the deeper problem remains. Reducing the mass energy requirement from a planet to a spacecraft does not solve the issue of what kind asterisk of energy is required. We do not know how to create large quantities of negative energy. We do not know whether large quantities can even exist in a stable form, or whether attempting to generate them triggers instabilities the mathematics hasn't fully explored. Some theoretical work suggests stabilizing a warp bubble may also require exotic matter material with genuinely negative mass, which has never been observed to exist anywhere in the universe. Not in a laboratory, not in deep space. Not anywhere. There is a second problem, unrelated to energy. As the warp bubble moves forward, compressing space ahead of it, any particles in its path, however sparse, would be swept up and accumulated at the leading edge. Over an interstellar journey, even through the thin interstellar medium we explored earlier, those particles would be compressed to extraordinary densities. When the ship arrives and the warp field deactivates, that accumulated material would be released as an extraordinarily energetic burst of radiation. Some physicists have described this as a potential planet-sterilizing event, capable of devastating the very star system the ship was traveling to explore. The warp drive may not simply be difficult to build. It may be physically incapable of arriving safely, even if every other obstacle were solved. This is the pattern that has now repeated across every proposal we have examined. Project Daedalus shrank from a dream of human explorers to a robotic probe. Breakthrough Starshot shrank further still, from a probe to a chip-sized sail. And now the warp drive, the one idea that seemed to offer an actual loophole in physics itself, reveals requirements so extreme that even its most optimistic version depends on a form of energy we have only ever produced in quantities too small to measure without nanometer precision laboratory equipment. The warp drive is not science fiction. It is real mathematics, a real, theoretically valid solution to Einstein's equations. But valid mathematics is not the same thing as an achievable engineering project. And there is one final, quieter problem worth sitting with. Even if every energy requirement were met, even if exotic matter were somehow discovered, even if the radiation burst were engineered away, the warp drive does not eliminate the loneliness we explored earlier in this documentary. A ship inside a warp bubble would still be isolated from Earth for the duration of the journey. Communication would still face the same speed-of-light barrier governing every signal in the universe. The warp drive solves the problem of time. It does not solve what distance has always meant for the people attempting to cross it. It would simply mean arriving sooner, not arriving differently. So we are left with a conclusion that feels strangely familiar. The universe has not closed the door on faster-than-light travel through warped space, but it has placed behind that door a requirement so extraordinary negative energy at a scale we have only measured in quantities smaller than the width of an atom, geometry so precise that a small error could prove catastrophic, and an arrival that current calculations suggest could be lethal to everything nearby, that the door might as well be sealed. For now, perhaps forever. And if warped space cannot offer humanity a true shortcut to the stars, there remains only one other idea radical enough to even be considered. Not bending the space between 2 points, but connecting them directly, a tunnel through the fabric of reality itself, where the distance between Earth and Alpha Centauri might not need to be crossed at all. It carries a name borrowed not from physics textbooks, but from the folds of a piece of paper. It's the wormhole. In 1935, Albert Einstein and a physicist named Nathan Rosen were studying the equations of general relativity when they noticed something strange hiding inside the mathematics. A solution that seemed to describe a bridge. Not a bridge of steel or stone, but a bridge through spacetime itself, a tunnel connecting two distant points in the universe, allowing something to pass from one location to another without crossing the distance in between. Today we call it the Einstein-Rosen bridge. Most people know it by a different name. It's the wormhole. The idea is easier to picture than the warp drive. Take a sheet of paper and draw 2 points on opposite ends. Walking from one point to the other means crossing the entire length of the page, but fold the paper in half and bring those 2 points together. Now a single hole punched through both layers connects them directly. The distance hasn't been crossed. It has been erased. If such a structure existed in real spacetime, a ship entering one end might emerge near Alpha Centauri instantly, having traveled no meaningful distance at all. No years of acceleration, no relativistic time dilation, no radiation-soaked decades drifting through the interstellar medium. Just a tunnel and a single step. For a brief, exhilarating moment, this feels like the answer the entire documentary has been circling. It is not. The mathematics describing wormholes comes with a condition every bit as punishing as the one we just left behind. A wormhole left to the ordinary physics of gravity is not stable. The same gravitational forces that would allow such a tunnel to exist would also cause it to collapse in on itself, instantaneously, the moment anything attempted to pass through. Physicist Kip Thorne, who studied this problem extensively in the 1980s, while consulting on what would eventually become the film Interstellar, demonstrated that holding a wormhole open requires the same exotic ingredient that haunted the warp drive. Negative energy, exotic matter. Something with genuinely negative mass, threading the throat of the tunnel, pushing outward against gravity's relentless pull to keep the passage from sealing shut. We have already established what that requirement means. The Casimir effect proves negative energy can exist, in quantities smaller than a snowflake. Holding open a wormhole large enough for a spacecraft would require concentrations of exotic matter on a scale physics has never observed, and engineering has no concept of how to produce. The wormhole does not escape the problem the warp drive could not escape. It simply relocates it. There is a deeper unease hiding inside wormhole physics, one that goes beyond engineering difficulty. If a stable, traversable wormhole could ever be constructed, the same equations that allow it to connect 2 points in space also appear to allow it to connect 2 points in time. Some theoretical work suggests that a sufficiently advanced wormhole, manipulated correctly, could become a path not just across the galaxy, but into the past. Physicists take this possibility seriously enough to have spent decades trying to rule it out, precisely because it threatens something more fundamental than travel itself. It threatens causality, the basic rule that effects must follow their causes. Stephen Hawking proposed what he called the chronology protection conjecture, suggesting the universe contains some mechanism, not yet identified, that prevents time travel paradoxes from ever actually occurring. No one has found that mechanism. No one has disproven it either. What remains is an idea so theoretically extreme that even the physicists most willing to take it seriously treat it as a mathematical curiosity sitting at the very edge of known science, rather than a genuine engineering proposal. So we arrive at the same place the warp drive left us. Two ideas, both legitimate solutions to Einstein's own equations, both technically permitted by the laws of physics as we currently understand them, and both requiring something, negative energy, exotic matter, concentrated in quantities and configurations no experiment has ever approached, that may not be obtainable by any civilization, regardless of how advanced its engineering becomes. The universe has not said no. It has said, only if you can violate in practice something we have never seen violated in principle. We began this journey with a beam of light, racing toward Alpha Centauri, 4 years from arrival. We end it in roughly the same place. Across everything we have examined tonight, the staggering scale of a single light year, the speed limit woven into the fabric of reality, the energy demands that grow exponentially as velocity approaches light speed, the quiet cruelty of time dilation that turns every interstellar mission into a one-way farewell, the slow transformation of a spacecraft into an entire civilization sealed inside metal walls, the radiation and dust that make even empty space a hostile ocean. The shrinking of every serious proposal from starships to probes to objects the size of a postage stamp, and finally the warp drive and the wormhole, the two most exotic loopholes physics has ever proposed, both sealed behind the same locked door of exotic matter we cannot produce. Across every single one of these obstacles, a pattern has emerged that is impossible to ignore. The universe has never told us that interstellar travel is forbidden. It has told us again and again in a dozen different forms that it is extraordinarily, almost unimaginably expensive. Not expensive in money, expensive in the fundamental currency of reality itself, energy, time, matter, and the exotic physics that may or may not exist outside the walls of a laboratory. This brings us back to the question we asked at the very beginning. If intelligent civilizations exist throughout the Milky Way, why does the galaxy appear so silent? Tonight offers an answer that has nothing to do with rarity and nothing to do with extinction. Perhaps civilizations are common. Perhaps they rise again and again on countless worlds scattered across the galaxy's 100 billion stars. Perhaps many of them survive their own adolescence, avoid the wars and the climate collapses and the technological catastrophes that might silence a younger species. And perhaps every single one of them eventually arrives at the same conclusion we have arrived at tonight. That the distance between stars is not a wall to be broken down with enough cleverness and enough time. It is closer to a property of reality itself, as fundamental and as unmovable as the speed of light or the curvature of spacetime. A civilization 1,000 years more advanced than ours would still face the same exponential energy curve as velocity approaches light speed. A civilization 1,000,000 years more advanced would still need negative energy in quantities no experiment has ever produced to hold open a tunnel that gravity is constantly trying to seal shut. The silence of the galaxy may not be the silence of absence. It may be the silence of everyone, everywhere, quietly discovering the same locked door. And yet, there is something worth sitting with before we close this chapter, because despair was never the point of tonight's journey. Project Daedalus was never built, but the engineers who designed it proved that interstellar travel, while almost unimaginably difficult, does not violate physics outright. Breakthrough Starshot has not launched a single sail, but laboratories around the world are, right now, testing the individual components, lasers, reflective materials, miniaturized electronics that such a mission would require. Harold White's experiments at NASA produced no warp field, but they represent the first time a national space agency treated faster-than-light travel as a subject worthy of careful, rigorous, fundable research rather than dismissal. None of these efforts have closed the distance to Alpha Centauri, but each of them has done something almost as significant. They have replaced speculation with mathematics. They have replaced maybe someday with specific numbers, specific energy requirements, specific engineering constraints that future generations can study, refine, and perhaps, in ways we cannot yet imagine, begin to chip away at. History offers a strange kind of comfort here, the same comfort we questioned at the very beginning of this documentary. We are right to be skeptical of the assumption that every barrier eventually falls to technology. Tonight proved that some barriers are not engineering problems at all, but the basic architecture of the universe. But within that architecture, humanity has already demonstrated something remarkable simply by trying. We have built spacecraft that left the solar system. We have measured negative energy in a laboratory. We have calculated in precise mathematical detail exactly what it would cost to reach another star, and found the number staggering but not infinite. Right now, that same beam of light from the opening of this documentary continues its journey, exactly as it has for the past 4 years, exactly as it will for years to come, racing silently toward a star system that has never once changed its position in our sky. It will arrive at Alpha Centauri having broken no laws, asked no permission, and required no fuel. It is, in its own way, already doing what no human spacecraft has ever managed. Perhaps that is the final, quiet lesson hidden inside everything we have explored tonight. The stars are not unreachable because the universe is cruel. They are distant because the universe is, on a scale our species is only beginning to comprehend, almost incomprehensibly large. And light, the fastest thing that exists, is the only traveler patient enough and humble enough to make the journey on the universe's own terms. We are not there yet. But for the first time in human history, we know exactly what standing in that light's place would actually require. And perhaps one day that will be enough.